Let's talk about something we do all the time, turning. In a car, on a bike. Heck, our planet is doing it right now. It feels totally normal, right? But here's the thing. In the world of physics, going in circles is actually, well, it's completely unnatural. In fact, it breaks one of the most basic rules of the entire universe.
Okay, think about this feeling, because I know you've felt it. You're a passenger in a car. The driver takes a sharp turn, and bam, you're slammed against the door. It really feels like some invisible force is just shoving you sideways, right? Well, what if I told you that force isn't real? That feeling, it's all an illusion.
And this is why. This is Newton's first law. You can think of it as the universe's default setting, inertia. Basically, things are lazy. They don't want to turn or speed up or slow down. If something is moving, it just wants to keep moving in a perfectly straight line, at the same speed, forever.
So let's go back to that car. The car turns, but your body, following Newton's law, just tries to keep going straight. The only thing that makes you turn is the car door literally getting in your way and forcing you along for the ride. So that sensation of being thrown out isn't a push at all. It's your own body resisting the turn. It's your inertia in action.
And that leads us to the big, central puzzle here. If the natural state of every single moving object is to travel in a straight line, how does anything ever manage to move in a circle? What could possibly be strong enough to constantly fight against inertia and bend that straight path into a curve?
Well, the answer isn't about pushing things out. It's all about pulling them in. We need a center-seeking solution. And here it is. Say hello to centripetal force. The name literally means center-seeking. This is the hero of our story. It's not a gentle nudge. It's a constant, relentless, inward-pulling force that grabs an object and yanks it away from the straight line it wants to follow. Without a centripetal force, circular motion just plain can't happen. Period. Now, here's the key thing to get your head around. Centripetal force isn't some brand new magical force. It's more like a job description. It's a role that a bunch of other more familiar forces can take on. Forces you already know, like friction or gravity, can be hired to do the job of being the centripetal force.
So how much force do you need to hire for the job? Well, that depends on three things: how heavy the object is, how tight the turn is, and how fast it's going. But look closely at that equation. The velocity, v, is time squared. That's a huge deal. It means if you double your speed, you don't need double the force. You need 4 times the force to make the same turn. This is exactly why taking a curve on the highway too fast is so incredibly dangerous.
All right, so which of our everyday forces are moonlighting as centripetal forces? Let's unmask a few of these forces in disguise. Let's start with your car again. When you're turning on a simple flat road, what's stopping you from just skidding straight ahead? It's friction. The static friction between your tires and the road is the force that's been hired for the job of centripetal force.
It's that grip from your tires that provides the constant inward pull, forcing the whole car to deviate from its straight path. And this is why hitting a patch of ice is so terrifying. The friction suddenly vanishes, the centripetal force is gone, and your car's inertia takes over, sending you sliding in a straight line right off the road.
Okay, but what about those big sweeping curves on a highway off-ramp or on a NASCAR track? They use a really clever trick. They bank the curve. They tilt the entire road inward. By doing that, the road itself actually starts to help you make the turn.
So here's how that works. The road is always pushing up on the car, right? Physicists call that the normal force. But on a banked curve, that push is no longer straight up. It's angled inward. A piece of that push is now pointing directly toward the center of the turn. It's helping friction do its job. The road itself is basically steering the car, which lets you take the turn faster and safer. Pretty smart, huh?
Now, let's zoom out, way out, from the highway to the heavens. For a planet orbiting the sun, there's no road, there's no friction. So who gets the job of being the centripetal force out there? Well, it's the most famous force of them all, gravity.
Because of its inertia, the Earth is constantly trying to fly off in a straight line into the cold emptiness of space. But the sun's gravity provides a constant, powerful inward pull, like an invisible cosmic tether. That gravitational tug is the centripetal force that bends the Earth's path into an orbit. You know, in a very real way, an orbit is just a state of constantly falling sideways.
Okay, let's bring all this physics back down to Earth and talk about one of the absolute best places to feel these forces in action, a roller coaster, specifically a vertical loop.
You know the feeling. At the bottom of the loop, you feel like you weigh a ton. You're crushed into your seat. But as you go over the top, upside down, you feel practically weightless, like you're floating. That dramatic difference in feeling is all about how the centripetal force is working with or against gravity. At the bottom, the track has to push up on you with a massive force. It has to fight gravity and provide the huge inward force needed to shove you up into the loop. That big push is what you feel as being super heavy. But at the top, something amazing happens. Gravity is now pointing down toward the center of the loop. Gravity is helping make the turn. The track doesn't have to push down on you very hard at all, so you feel incredibly light. Okay, it's time. We have to address the single biggest misconception about circular motion. People have a name for that feeling of being thrown outward, but I'm here to tell you it's a phantom. It's a ghost. And hey, don't just take my word for it. The physics textbooks are super clear on this. Centrifugal force, that supposed outward pushing force, is a fiction. It flat out does not exist. It's a phantom force born from a misunderstanding of what's really going on.
The whole confusion comes down to your point of view, or your frame of reference. If you're on the merry-go-round, you're in a spinning, accelerating world. To you, it absolutely feels like a force is trying to fling you off. But if someone is standing on the ground watching, they see the real picture. They see your body trying to go straight, and the ride constantly pulling you inward to keep you moving in a circle.
So let's just break it down one last time. Step 1. Your body has inertia. It wants to go straight. Step 2. The ride you're on forces you to change direction constantly, pulling you into a circle. And step 3. That feeling of being thrown out is just your body resisting that change. It's the ghost of the straight line path your body wishes it was on.
So if you remember one thing, make it this. There is no outward centripetal force. There is only an inward centripetal force. It's not some outward push, it's the inward reality that's required to make anything turn at all.
And this leaves us with a pretty mind-bending final thought. That same exact principle, that phantom force that's really just inertia in a rotating system, is also what causes the Coriolis effect on our spinning planet. It's the invisible hand that gives hurricanes their spin. It makes you wonder, what other profound invisible rules, all rooted in simple laws like inertia, are secretly shaping the complex, beautiful, and circular paths of everything in our universe?